So aerobic metabolism. Aerobic is, in many ways, much more complicated than all of our anaerobic pathways. Okay? I don't want to say it's better, it's different. We get a lot more energy out of it, but it's way more complicated. We can break down a larger variety of energy substrates as well. But because of that, it's also more complicated, because each of those things go through some common pathways, but not everything is going to be common between carbohydrates and fat. Okay, so it's most basic. It's the breakdown of glucose, fat, or protein to carbon dioxide, water, and ATP. We have to remember that we make CO2. Okay, we've got to remember that we're going to make CO2. That is going to get synthesized with this, and it requires oxygen. Okay, and it requires oxygen. That's the other key thing. Although, to be 100% honest, I think we make a big fuss over the oxygen way more than we should. Because for most of you guys, the oxygen's not ever going to be a problem unless you want to exercise with blood pressure on, or you want to go to base camp at Mount Everest or someplace. Now, in older individuals or people that have end-stage COVID or asthma or some kind of pulmonary deficiency, then the oxygen becomes way more of an issue. Okay? It mostly uses glucose and fat. And if you supply glucose and fat and oxygen to these pathways, our capacity to generate energy is basically limitless. And what I mean by that is we don't make anything. Okay, we're limited with creatine phosphate because we just have X amount of creatine phosphate. And once it's gone, it's gone. We're limited with free ATP because we have X amount of free ATP. We're limited in glycolysis because of the hydrogen ions that we make from the dissociation of lactic acid into lactate hydrogen. The hydrogen can feed back into our various pathways and other parts of the muscle contraction pathway and inhibit things and make us stop exercise. We don't make anything with aerobic metabolism that's going to cause the process to stop. Okay? CO2 it's a metabolic waste product, but it's not something that inhibits metabolism itself. It doesn't inhibit contractions. Okay? It doesn't inhibit cardiovascular function. It actually ramps up breathing. And so it's going to function to help kind of rid itself. Water doesn't do that. Okay? The issue with aerobic metabolism, and this is where it's going to play a ginormous role, the ability from a speed standpoint of this to function is going to play a big role in aerobic exercise, kind of endurance exercise performance, as well as some recovery kinetics after you've stopped doing anaerobic exercise. It's slower because it has many, many more steps. And in theory, it's limited by oxygen delivery. Okay? Although in healthy young people like you guys, O2 delivery is rarely ever over. It's a thing we need to be concerned about, but it doesn't, in some populations, it's not ever going to be a real thing. Okay? I'm going to break aerobic metabolism into 3 steps because each of these steps is going to generate a couple of things. And I think it's the easiest way in my mind for you guys to separate it out and kind of conceptualize it in the big picture. So we are going to bring aerobic metabolism. We have to get the pyruvate, all right, from the second to last step of glycolysis. We want to get pyruvate, and it needs to get into the mitochondria. We are going to do that by making it into acetyl-CoA, not actyl-CoA. I don't know why in the hell I spelled it that way. Clearly, I was drunk when I put these together. But we're going to have a step that we're going to call this intermediate step, where we're going to convert pyruvate into acetyl coenzyme A. That acetyl coenzyme A is then going to go into the Krebs cycle. We're going to work our way through the Krebs cycle, make some carbon dioxide, make some ATP, reduce a huge amount of electron carriers, and then those electron carriers are going to go to the electron transport chain and donate their electrons. Okay? If you care a huge amount about all of the kinetics of this, and this thing is here and there, and this enzyme, then go take biochemistry. Okay? You'll get a huge amount of stuff on all. We're going to hit the high points. What we really want to focus on is where are the pinch points in this? Where is it the slowest? Where is it the fastest? Okay? How are we going to figure out whether this pyruvate is going to go here into acetyl-CoA, or that pyruvate would go to lactic acid? How do we balance those kinds of things? Okay? How do we make it so that we have more or less Krebs cycle enzymes to go and do things? And then with the electron transport chain, depending upon where things enter, why is that going to play some role in the amount of ATP? Of course, now this thing doesn't want to work. Ta-da, Krebs cycle. I'm sure you guys have seen this 1,000 times. It's sometimes called the citric acid cycle. But what we've got is here we have pyruvate, which is a 3-carbon molecule. To get to acetyl coenzyme A, anybody? Biochemistry, organic chemistry? Remember acetyl groups, 2 carbons. Okay, 2 carbons. So we're going to go from a 3-carbon molecule to a 2-carbon molecule hooked on to a coenzyme A. Don't worry about the CoA, it just helps us to transport things. That will become important later when we talk about fat metabolism. So 3 carbons to 2. So we've lost a carbon. Guess what happens to that carbon? We make CO2 out of it. It binds to oxygen, and voila, we get CO2. Okay? So we have a pyruvate, we split a carbon off, we're going to grab some electrons from that oxidation reaction. We've now made this acetyl group, we hook it to coenzyme A, that gets shuttled into the mitochondria, and voila, now we're going to go through Krebs cycle. We've got citrate, an isocitrate, an alpha-ketoglutarate, succinyl-CoA, right, to succinate, to fumarate, to maltate, to oxaloacetate, and the whole thing starts over. Important things to remember, okay? 2 carbons in the acetyl. Oxaloacetate has 4 carbons, okay? 4 carbons at the very end, added to 2 carbons coming in from outside, and we get a 6-carbon citrate molecule. So if we're going to go from 6 to 4, we're going to lose 2 carbons. So we're going to make, you guessed it, 2 more molecules of carbon dioxide. Move here at citrate, we're going to go from isocitrate to alpha-ketoglutarate, from alpha-ketoglutarate to succinyl-CoA. These 2 things here. Okay. As we lose the carbons, we're going to grab some more electrons at this step and at this step. Okay, they're going on to NAD here. As we move a little bit farther along, as we go from succinyl-CoA to succinate, we're actually going to do some straight up substrate phosphorylation where we're going to grab a phosphate group off and make a molecule of GTP, which then through some biochemical processes gets converted to ATP. What it really is GTP. We borrow the phosphate from GTP and put it on the ATP. But the net down here is, look, I've made CO2, I've reduced electron carriers, I've made some actual ATP. Okay. Then we're going to go from succinate to fumarate. We're going to get some more electrons, even though we're not losing a carbon molecule here. In this one, they're going to bind to a different electron carrier called FAD. Then from malate to oxaloacetate, we're also going to get even more electrons. We're going to come back on here. I meant to look up today, and then I got busy as to, well, why do we use FAD here and NAD is at the other steps? And I do not recall off the top of my head. Anybody remember from biochemistry why that is? I'm sure it's something about the charge and the way that these things are going to go and the affinity for the electron that's different between NAD. I'll try to look that up for you guys for the next step. Okay, so let's do some math. Okay, pyruvate, we're going to have 2 of those. Right, 1 molecule of glucose is going to end up with 2 pyruvates. So we're going to go through this twice. So for each one, we've made 1 molecule of CO2, 2, 3 molecules of CO2. We have netted 1, 2, 3, 4 NADH molecules and 1 FADH molecule plus 1 ATP. Okay, so we do that twice. So we're going to end up with 8 NADH molecules, 2 FADH molecules, 6 CO2 molecules, and 2 ATP. Okay? That's what we're going to get from all of this. And we're going to use the NADH and the FADH and the electron transport chain to help us make a large amount of ATP. Okay? But we have actually netted some. So we net as much ATP from the Krebs cycle as we do through glycolysis if it was from a molecule of glucose that's coming from the bloodstream. Okay? So we're going to get some out of all of this. So things that I want you to be aware of. So this enzyme here that takes us from succinate to fumarate is called succinate dehydrogenase. This is abbreviated as SDH, and this is one of the most, if you look in older papers from the 70s and the 80s, this is one of the enzymes that people look for in muscle biopsies to try to denote aerobic sort of metabolic capacity. Okay. If you have more SDH, then that means you have more mitochondria, you have more Krebs cycle machinery, and that would mean sort of higher endurance capacity, or at least a higher capacity to make ATP in sort of Krebs cycle and mitochondria. Okay, this is not the rate-limiting enzyme, alpha-ketoglutarate dehydrogenase. This is the rate-limiting enzyme, I believe, or maybe it's isocitrate. It's isocitrate, isn't it? Yeah. Sorry. So you will note that I've not really ever taught this before. Our Dr. Mike, our department chair, when he teaches the undergrads, didn't teach this until 2 years ago. Our undergraduate quiz bowl team that participates in the American College of Sports Medicine lost the National Quiz Bowl Championship because we never taught them that this was the rate-limiting enzyme website. They were winning going into the very last question, which is do a Jeopardy style. They were winning by a lot going into Final Jeopardy, and they didn't know this because we never bothered to teach it to them. So
who won it?
Yeah.
Who won?
Who won? I don't remember who won. At that point, I didn't care. I think it was maybe somebody from App State, or one of the team from the Southeast. Maybe it was App State or Kennesaw, someplace in the Southeast. I just know that our kids were very disappointed. And I was disappointed because we hadn't bothered to teach it to them. So anyway, I think it's isocitrate. So here we go. Slowest step. You can't really do a lot with isocitrate dehydrogenase, unlike some of the glycolytic enzymes to make them go faster or slower. Okay, so we've done all of this. Let's talk about the electron transport chain. Okay, so they're going to be located on the inner membrane of the mitochondria. They're going to contain things that we call cytochromes, which have iron in them. Iron is a +2 charge. Iron is very, very, very attracted to electrons. It wants to grab your electrons and hold them for you. Okay, and so by having these sort of cytochromes in this chain, there are going to be several of them. We're going to pass the electrons from one to the other. We're going to use that to create a concentration gradient where we pump hydrogen ions out of the mitochondria to create a concentration gradient. Again, and that runs, the energy from that is going to run, diffusive energy runs this enzyme called ATP synthase, and we're going to use that to stick phosphate back on. This electron transport chain, key thing with oxygen is that the train passes the electrons, ping, 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 down, okay? Here, 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 here. Here's the ATP synthase at the very end. What happens is it's going to pass these electrons down, 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 and it gets to the very end, and those electrons have to go somewhere. So we then give them to oxygen, because oxygen, very much like iron, is going to want those electrons. And we donate them, oxygen binds them, then oxygen picks up some of its hydrogens and forms water. Okay? We use the energy from allowing these hydrogen ions to get built up out here to fuse back down that gradient, the concentration gradient into the inside of the mitochondria. That runs this enzyme. Make ADP, we make ATP, when we shuttle ATP and we get this translocase back out of the mitochondria so that we can use that ATP in our cells. Okay, so there we go. Here we have the matrix. This is the inside, right? This is the inner mitochondrial membrane on this. We're making our pyruvate. I kind of like this. this version. Looking at things, this also illustrates if we've got fat that needs to be oxidized, we're going to move the fat in a different way from how we're moving the pyruvate in, but it eventually ends up binding out as acetyl-CoA, and it goes into the Krebs cycle just like pyruvate. And we'll talk about beta oxidation today, probably on Wednesday. Okay, here's the electron transport chain. The key thing that I want you guys to know about all of this, and the reason that we're going to make a different amount of ATP from electrons that come from NADH than those that come from FADH, is where in the chain they donate there. So NADH is allowed, it will give up its electrons at the first cytochrome here, okay? And then those electrons essentially from there bypass cytochrome 2 and jump to cytochrome 3, whereas the electrons that come from FADH get donated at number 2. So they're not moving as far down this chain. So they're going to pump, in theory, then less hydrogen across. As you will note that when we donate some at 1, we're going to get some hydrogen here. We don't get much that moves at 2, we're going to get some that moves at 3 and at 4. So when we donate at 1, you're going to get this extra stuff. So it helps us move up a greater gradient out here in this outer sort of compartment. And then those are going to diffuse back through the ATP synthase, and that's going to drive. So I will back up. The way the math works, again, I think I mentioned this last week. The math is weird, and I don't like it. It's not how I was taught. This is the new math, and it's technically more accurate, but it also, to me, is more confusing. We're going to say that for every NADH molecule that we're going to bring into the electron transport chain, we'll make 2.5 ATP. So that means half the time it makes 2, the other half the time it makes 3, so we end up with that. I was taught you make 3, but that's okay. This is a little more accurate. And then for every FADH molecule that comes in, you're going to make 1.5. It's going to come in. So half the time you make 1, the other half the time you make 2. Okay? That's how the chain is going to work. Here's where I have done, and I have tried to say, we're going to do some accounting for the things that we make from a molecule of glucose that has come from muscle glycogen. Okay? So we've got a muscle glycogen molecule of glucose. It's going to go through glycolysis, right? We're going to get to the pyruvate state. As we've done that, we've made, because it's from glycogen, we've made 3 ATP, and we've generated 2 NADH molecules. Okay? We've also generated 2 pyruvates. So as those pyruvates get turned into acetyl-CoA, we make 2 more NADH molecules. We go through Krebs twice, so we make 2 ATP directly, 6 NADH, and 2 FADH. So we can do all the math here, right? We've made 5 directly, and 12, 15 from our NADH, and 3, so that's 18, and 5, right? We're going to add all these things up. Add all these things together, you come up with about 34 ATP. Okay? If we do all of them. So that's how we're going to end up doing it. Okay. Questions about that? That's the pathway, right? As I said, we could go into the biochemistry of the whole thing, and it all happens via these concentration gradients, and the reactions are all in many ways passive, and then it's just sort of what's going to move into what. But a lot of it is driven by ATP and ADP. Okay, so we're going to do a little bit here in the middle and talk about how we measure energy use, how do we try to quantify aerobic metabolism, and why we can't quantify anaerobic metabolism, and how that's going to relate to some things in exercise. Okay. So if we look at our energy generation equation, at least aerobically, we're going to take, for example, glucose. This could also be a different kind of carbohydrate, or it could be fat or lipid. We're going to have our substrate plus ADP plus oxygen, and we're going to get ATP, carbon dioxide, water, and heat. So when we want to measure energy use, the best way to do it is to measure heat directly, right? I'm going to make Richard get up and do jumping jacks for 5 minutes, and then we're going to have Cy stand next to him and be like, is he getting warm or not? Like, is his temperature changing? He's giving off heat. No. If we can measure how much heat production there is, then we can back calculate approximately how much substrate we're using. Conversely, because that's kind of hard to do, we can make an indirect measure of things, and we can look at what we're going to call a metabolic byproduct. We can essentially measure carbon dioxide production and look at that in its ratio to oxygen use, and from that we can also then back out. Okay. It is nearly impossible for us to measure anaerobic metabolism. Nearly impossible. I'll talk about how historically they thought they had a way to do it, and they were wrong. Okay? But it's nearly impossible. So anytime we talk about things, we talk about energy expenditure, all we're really talking about is aerobic. Okay? So if we want to assess things, the best way to do it is called direct calorimetry. We convert about 60% of our energy into heat. We're amazingly inefficient in that way. But we're also, because of that, really, really good compared to other animals at dissipating heat. Okay? If you guys couldn't dissipate heat, you'd kill yourself within an hour. You'd overheat, you'd cook the brain really well. Okay? So if we measure heat production, we can estimate energy use. The calorimeter that they use, I don't think we have one of these anywhere in the state of Oklahoma. Closest one that I know about is at the med school at the University of Arkansas in Little Rock. They have one, but it's an insulated room basically with airtight. So it's airtight. The walls have copper tubing, and it runs water through the copper tubing in the walls. You make heat, it goes through the wall, and it heats up the water, even a tiny, tiny amount. We know the specific heat of water. We know how much heat it takes to raise the temperature. 1 milliliter of water, 1 degree Celsius. From that, then we can calculate how much heat you produce. So you sit in this room, or you exercise in this room for a week or for a couple of days, and they feed you a different diet, or they have you exercise in different ways, or whatever. You just live in this room, and they can quantify your energy use. It's not a great way to assess, like, okay, I'm going to start biking right now. I want to figure out what my metabolism is. It's not super great for all of that, but it's very useful for trying to understand very accurately kind of resting metabolic rates and the effects of some of these other things that can help. Okay? They have these that are very small. They don't simulate regular free living very well. They have some very big. And so one of the limitations is it doesn't sort of, it's not very ecologically valid. It doesn't mimic what a person would do in their everyday life. But they have one, I think it's in Germany, maybe in Switzerland, that is in essence a mock-up of the International Space Station. And the whole thing is a calorimeter. And they stick some of the astronauts in there for like 6 months at a time before they send them up into space. I saw a presentation about it at our national meeting, because they're worried, like if you're going to go to space and you freak the fuck out, they can't do anything. You're stuck. You're in space for like, 6 months or whatever. So they want to make sure that you can, even though it's not simulated weightlessness, they want to at least make sure that you're going to be okay, sort of in confinement and those things. And they're interested in at least with gravity, what's the energy demand of various tasks and these kinds of things. And then they can say, if we take gravity away, it's going to change in this kind of relatively predictable manner. So they can estimate, okay, a person that weighs this much in this, they need to send this much food and all of those kinds of things. So pretty fascinating. Okay. It's not great for doing shorter, more intense exercise. So here's kind of what a calorimeter is going to look like. I don't know why she has such terrible posture. I don't know why she's wearing, I guess those are shorts. I don't really know. Right? Who knows? This is just kind of how it works. Okay. Pardon?
Are there environmental chambers that are?
You're also that?
Yeah.
Yeah.
Okay.
You could make the chamber. So what Chris is asking is, could it be an environmental chamber? And by that we mean, could we very accurately change the temperature and the humidity inside those particular rooms? Yes. Okay. Although most environmental chambers are, but you could do that.
Okay.
Yes. Okay. So indirect calorimetry is much, much, much more common. Okay. If it wasn't such a pain in the ass, I guess I could have made several of you guys go downstairs and haul our metabolic cart up here for a demonstration. Like all of our labs, everybody's lab has their own. It's called a metabolic cart. It's what it is it's an indirect calorimeter. but it's an analyzer that analyzes CO2 production and oxygen in the air that we're breathing out. And we make some assumptions based upon all of that. And so we can say by the change in the ratio of CO2 to O2 in expired air versus what's in inspired air, we know room O2 and room oxygen. And we collect what you breathe out, then we can back calculate basically what we think, how much oxygen we think you're using. And if we know how much oxygen we think you're using, we can guess at both what substrate you're breaking down and you're breaking down carbohydrates and fat, how much you. Sarah.
So there's this new thing, it came up on my Instagram ad. It's like it's this size and it's black, and you breathe in and out. It's just telling you, like, I guess your metabolic rate, and then based on that, you can adjust like what you eat, or like what foods you should be eating. So
Is that real? Is it doing what this thing is? I don't know. What I would say is that like one breath, especially the way most of these things work, one deep breath is actually going to give you a very inaccurate assessment of things. Most of them are, they have to try to control for breathing volume. And so you need to do things, especially if you want like resting rates, you need to do them. One breath can give you a very homogeneous kind of especially because it's very hard. If you're over breathing, you're breathing off more CO2. But if you find it, or if you can find it, email it to me. I'd be fascinated to look at it. I would argue that if we know what your body composition is, we know what your resting heart, we know what your heart rate is, you can probably do just as good a job at kind of making some guesses off of those things. Energy expenditure.
So it's like the breathalyzer one, yeah?
Yeah, what's the little breathalyzer?
Yeah. And you're supposed to, it sounds like a breathalyzer, just breathe out for an extended period of time. So. I know what you're talking about. I don't
Yeah,
know
I
what
thought it was like, what?
Yeah.
Okay, interesting. So this introduces two terms. But I can't remember if we've talked about these at all before. Again, I'm confused with my undergraduate class because there's all different things, but it's called VO2, which is oftentimes called oxygen uptake or oxygen consumption, and then VCO2. And so the V in these things stands for volume. It's the volume of oxygen that is, we call it uptake, but it's really consumption. How much oxygen are we consuming by muscles and other tissues in a given period of time? So what that's going to tell us then is what is your aerobic metabolic rate, right? Based upon how much oxygen is being used in this particular tissue. And then the CO2 is the volume of expired CO2 that we're able to collect. These are usually expressed initially as liters of oxygen that are going to be consumed every minute, or liters of CO2 that are going to be produced every minute. We actually normalize VO2, we normalize the O2 one to your body weight most of the time. And so it ends up in the units are kind of weird. It's milliliters of oxygen consumed per kilogram of body weight per minute. We'll talk a little bit about why that's important. People have expressed this in a whole bunch of different ways historically. There's some folks that think you should express it relative to lean tissue mass. So we started to go get a DEXA and calculate our lean tissue mass, and you should express it against the actual amount of tissue that you have that will consume the oxygen, and that will tell us one thing. If you're going to do weight-bearing exercise, it's much better to normalize it to total body weight because you have to lose all of the weight of the body. A lot of it is adipose tissue, and you still have to generate force to move it. So who cares? So there's some differences that are going to go into all of this. Okay. One thing to keep in mind. All right, and it's a pretty reasonable assumption, but what we are measuring when we are measuring expired air. And so let me see if I have a picture. Do I have a picture of this? Of course I do. Again, you all have probably seen like a shoe commercial or a Gatorade commercial or something where the person nowadays, a lot of times they have a mask that looks a lot like this. The mask sits on there There's a little thing in the front, it connects to a tube, the tube runs off and connects to our metabolic cart. And the person's running on the treadmill or they're on a bike or something. It used to be, and we still have these, but you had a mouthpiece. You would make like a football or like a sport, like thing you would bite on. That would go in. And then you had a thing that looked like what you would put on when you fractured your skull, but like a hat that would sit on there. You would cinch it down, and then it had these plastic things that would come out that would be adjustment and would hook onto either side of the mouthpiece. And you breathe in from one side, had a one-way valve where you could breathe air in from one side and only breathe air out from the other side. And so you would sit and breathe that way, or you would run or you would bike. We've gotten better at the technology. The old mask didn't seal around the face very well, so we've gotten better. But the assumption is that what we are measuring in expired air is directly proportional to what is happening with what's being brought in, our ability to diffuse things across the lungs into pulmonary capillaries, and then from the capillaries at skeletal muscle into skeletal muscle, and then what's coming, the CO2 and stuff coming out of skeletal muscle. We're very, very efficient. It's essentially a one-to-one ability to diffuse through all of those places. Off. That's a relatively reasonable assumption in most people. It's not going to hold anybody. So that's what we're kind of doing. This is much less expensive, even though it's still quite expensive compared to a calorimeter. Metabolic carts that we have downstairs, like everybody's lab has one. My guess is that through Jordan, you guys probably have access to one somewhere. Cart. The one that we have is about $20,000. You can buy some that are 5 or 6. They make some that are small enough that they can be portable. You put them in a backpack or a fanny pack or something, and have somebody go walk or run around campus. They may not want to, but they can do that. When I was a grad student, we had to, for one of our labs with the stuff, we would put on the portable one and go walk around campus as a group. That way, that was a super fun day for a guy with anxiety like me. Like everybody was looking at you thinking, what the hell are these people doing? But we can make these measurements. They're very accurate. I mean, they're not as accurate as direct calorimetry. It's very accurate for our ability to do these kinds of things. If you want to know your resting metabolic rate, this is the best way to do it. Come down to our lab or the other labs. You actually sit under we have a hood. You come down, you lay down, you go to sleep. You put a hood, like a plastic bubble over your head. You breathe into that. And okay. So this is whenever we talk about oxygen consumption, we're going to talk about what happens with aerobic metabolism during exercise, how it changes at the start, how it changes at the end. What we are measuring and talking about then is this number. Okay. For VO2. We're going to talk about this in a couple of ways. One thing we will talk about is maximal VO2. What we mean by maximal VO2 is the largest amount of oxygen that you can take up at your lungs, diffuse into your blood, and then diffuse into the muscles that can be used in the mitochondria to resynthesize ATP. Max VO2. So the larger this number, then that's usually measured during kind of high intensity all-out exercise. Max VO2 is the single best measure of aerobic metabolic function as it relates to endurance performance. Okay. So what it's going to tell us is what's the top end of things that you can do, what's the top end of energy that your body can produce aerobically. Okay. We're also going to talk quite a bit about something called submaximal VO2. Submaximal VO2 is just a way for us to try to quantify in any kind of activity that is not maximal, how much oxygen is required to generate the energy that is required for that. So y'all are sitting here. You have some submaximal VO2. We're all consuming oxygen right now. We're all contributing to the heat death of the planet as we speak. Yes. Okay. Whatever. I'll be gone before you guys. Whatever. Right? My daughter will be here after you guys eat. Terrifies me. time she's old enough, we're gonna have to live on top of Mount Everest, I guess, with all the oceans, we'll all live underwater. Anyway, there's those numbers. You go walk, your VO2 goes up. You've got some VO2 that we can measure. You're jogging, your VO2 goes up even more. We can measure all of that. Okay, so there's ways that we would talk about how that plays out, and what that tells us about metabolic function, what it tells us about cardiovascular function. Okay, so energy use, so exercise intensity. Remember I told you guys that exercise intensity determines substrate use. Exercise intensity determines the energy pathway that we use. Okay, so in that way, intensity is defined as work rate. It's how much energy do we need to work at a certain rate. So the more energy we use, the higher the intensity. Okay, work rate is proportional to muscle being used to generate force. Therefore, things that require more force require more muscle and to be used, and we have to run the cross-bridge cycle more, and we need more ATP. Therefore, we use more oxygen, and we use more phosphate. Okay, VO2 increases in a relatively linear manner with an increase in energy. So if you go from rest to walking, to jogging briskly, to sort of almost sprinting, to sprinting, your sort of force output from your muscles goes up like this, and correspondingly, your oxygen consumption, your aerobic metabolic rate is going to track right. Okay? So if there is some submaximal VO2 required, some submaximal energy use required, in some work rates, depending if they're not super duper high, you will reach what is called a steady state. It goes up and then it levels off and it stays right there. Okay? Up, level off, stay right there. We had Ethan stand up and start sort of walking in place for us. It's going to go up a little bit and then it's going to level off. We'll reach a steady state. However, if we ask him to get on the treadmill and jog very briskly for us, it might go up and kind of level off, and then it won't ever be able to truly plateau. It will kind of creep up a little bit over time. Okay? As intensity increases, we will get to a point at which it will not be able to achieve a steady state. It will sort of drift on us a little bit. And if we keep going, it will drift until we reach our maximal oxygen. That drift is called a slow component rise in O2 consumption. Okay? And it's going to denote a particular exercise intensity. It's going to denote a particular thing, in many ways, our inability to adequately make enough energy from aerobic metabolism to meet all of our energy. So there's some things that go into it. Okay, so this is kind of a complicated graph, and I apologize for that. I'm kind of mixing two things together just because I like the VO2 graph. But here's a person who's on their Peloton bike. Okay, all of you guys have a Peloton, right? Yeah. Seriously, you do? So
Yeah.
Y'all, do you personally have one, or do y'all have some in athletics?
No, when COVID hit.
Okay, sweet. There was a used one on, they allegedly had been used like twice on Facebook Marketplace in the city the other day. And I almost, it was only like a couple $100 less than what you could buy for a new one, but you can't get a new one because they're like back ordered for like 6 months. So if you didn't have to subscribe for like $60 a month to the thing to be able to use it, then I would be in. You like it?
I love it.
Because they yell at you, like, just freaking, let's go, work.
Yeah, if you get one, put your feet is my favorite.
If my wife liked to ride the bike more, we have a treadmill. I hate walking and running on a treadmill. It drives me up the fucking wall. I would be okay with being on the bike and doing those kinds of things. She hates the bike. If we would both use it, we'd just get one.
And subscription's not just for bike
I know,
instruction.
you can
get
get
all the videos for like 2-4, strength, yoga.
lots of things. You can also Peloton on a treadmill now too. They have treadmills.
Something on a rowing machine too.
I think so. Got one. So, anyway, okay. Anyway, you're on your Peloton bike. You're sitting here and you're resting. There's some amount of aerobic energy use. We're down here, okay? Then we're going to increase the power output. You're at 100 watts, you're at 200 watts, you're at 300 watts. So as this progressively goes up, then you will note that what tends to happen is we're going to get this relatively linear increase in oxygen consumption. Corresponds. You will reach some point, though, where I get to here and you make me work harder and my VO2 does not go up anymore. Okay? We call that a plateau. And this intensity right here, or this VO2, that number, that is your VO2 max. Right? We've made you do more work. You've had to generate more force. You needed more energy. But aerobic, our measure of oxygen consumption, our aerobic energy expenditure did not go up. Therefore, where did the rest of that energy have to come from? Anaerobic. So we've maxed out aerobic, so this is what we would call it. Okay? This is just showing sort of the corresponding increase in lactic acid. It's going to go along with that. We'll get back into that a little bit. Okay. Here's the slow component rise, and here is steady state. So we flipped our axes. We still have O2 consumption here. And then we have 5 minutes of exercise at 50 watts, 100 watts, 150, 200, or 250. So note, see here, in about a minute or thereabouts at 50 watts, I go up, I get to a steady state, and it stays the same. Work rate doesn't change, so O2 consumption doesn't change. 100, it takes me a little bit longer to get to steady state, maybe a minute and a half or thereabouts, but again, it stays. At 150, in people that are more fit, they'll plateau. But in people that are less fit, it comes up. It's taking me 2 minutes to get here. But see how it just kind of creeps on us? This is that slow component rise. It's more pronounced at 200. Okay. And then people that are at 250 really are going to have even kind of the same sort of, you're never going to get what you would think it would be here. It just kind of stays like that. Okay. Each of these things can tell us certain things. The shape of your slow component rise, the actual slope of your slow component rise can tell us things about your fitness. The intensity that it takes us to get to those things is also going to be the work rate. To see that is also going to tell us some things. Okay. But a lot of that is well beyond what we ever covered in this class because we're just kind of trying to get the basics. Okay. Okay. Something else to keep in mind here that's actually useful for us. Okay. You can calculate something called the respiratory quotient if you were able to measure it in the cells, or when we measure it in expired air, that's called RAR, or the respiratory exchange ratio. What this is CO2 production divided by oxygen consumption. Okay? And so, or expired CO2 divided by O2 consumption. What these two things, which are their scale is the same, what they tell us is what substrate are we metabolizing in order to get the ATP, aerobic ATP production? Okay? And so it reflects this estimate of non-protein substrate utilization. So you get values for this. If all you were doing, okay, was breaking down carbohydrates, then the amount of CO2 that you produce at the end of the Krebs cycle is going to be exactly equal to the amount of oxygen that you're going to need in the electron transport chain. So you have a value of 1.0. If you have only fat, okay, which is really never the case, I don't care what kind of crazy keto shit you're on, right? Then it's about 0.7, which means you are, for every CO2 that you are making, you're using more O2 at the end, or you're basically making less CO2 for the amount of O2 that's being consumed. Okay, so fat is 0.7, carb is 1. I get an RER on any of you guys, and let's say you're 0.85. That means you're at 50-50. Right? Where you fall in that range tells us how much of what you're breaking down is carbs, how much of what you're breaking down is fat. You can alter that by feeding you more carbs. I can make your RER go up. If I feed you more fat, I can make your RER go down. Okay? Your RER will change over the course of 3 hours of steady state exercise. And that's going to reflect for us breakdown of what glycogen, breakdown of adipose tissue, kind of where things are coming from. It will be different if I give you Gatorade or some kind of carbohydrate substrate while you're going for 3 hours, 5 hours, whatever. So it can give us some really useful information about kind of what all is going on. Okay, so we talked about max VO2, we talked about how we express it. All right, so let's think about max VO2. Okay, maximal oxygen consumption is highly related to total muscle mass, heart size, blood volume, and mitochondria in muscles. You use oxygen to propel yourself in muscles. Okay? If you have more muscle, you can generate more force, which means you can use more energy. Therefore, you will have more total mitochondria in your body. So total muscle mass matters. All right? It's one of the reasons that when we get a maximal O2 uptake value, we try to express it via body weight. So for that reason, because total muscle mass matters, sex matters, body size matters, weight matters, age matters, because all of these things can affect how much muscle, how much fat you have relative to body weight. Sarah.
At rest, you have more muscle. Are you using more oxygen to like keep that up?
Yes. So you're using, in an absolute sense, which we express here, your liters per minute of O2 use will be higher. Typically at rest, though, if we take your we express it relative to body weight, everybody is about the same. Everybody's resting VO2 is going to be somewhere between 2 or 2.5 mLs per kg per minute of O2 consumption in the body. Just really kind of depends. So, but if you're a person with more muscle, they will use more absolute O2 relative because they're bigger. So when we normalize it to body weight, they all kind of line. That makes sense?
Question.
Yes, ma'am.
So on here it says aerobically training, so level of aerobic training.
Yep.
So if we have two individuals that say hypothetically have the same amount of muscle mass,
Mhm.
but they're training, one is training endurance-ly or training via endurance, and then the other is training, say, resistance exercises, would they technically have the same VO2 max?
Absolutely not.
No?
Absolutely not.
Okay.
Because heart size, which is going to primarily determine their stroke volume, which is going to be the thing in your identical people that's going to separate their cardiac output, and their blood volume and the number of mitochondria are going to be very different.
Okay.
Right? So people that undergo aerobic training, okay, that's going to provide a fairly reasonable stimulus to increase, especially left ventricular size, which makes their overall cardiac output. It also stimulates their blood volume to increase. Their increase in blood volume is going to increase something called preload, which means they can dump more blood back into the left ventricle, which also makes their stroke volume. So these two things are going to allow them to have a larger cardiac output, which means they can deliver more oxygen to that muscle. And because they use and tax aerobic metabolism so much more during their training, that's going to stimulate mitochondria to sort of go up in those muscles. So I increase my capacity to use oxygen and to keep O2 low in the muscle, thus maintaining a very large diffusion gradient. And because of this, I can deliver more oxygen to those muscles. Now I can use more, and then that's what makes it
Okay. Thank you.
And we've now just covered the entirety of, that is, there's exercise physiology right there. There's integrated physiology, there it is, all the systems working together. muscles, the metabolism, cardiovascular system, respiratory, and pulmonary systems all together. So there we go. And training responses. All in one. Very good. Matt, you had a question? I answered it. Okay.
Is the carrying capacity of the
Yes.
same amount of blood change, right, with the rate of hematocrit?
Assuming their hematocrit changed, which it probably would with air change. For the same blood volume, people that are aerobic trained tend to have more red blood cells per total volume. Their hematocrit percentage goes up, which means their O2 carrying capacity is higher, which means that diffusion gradient in theory is going to be larger, so they can drive more. That gets to be wonky because things happen during exercise where we blow plasma out of our blood into the interstitial space and hemoconcentrate it anyway, and yeah, and then it gets complicated. Heart rate goes way up, and so blood velocity goes way up. It's moving too fast to be able to diffuse, and women have different carrying capacity than men. And it's a whole bunch of things. So again, it depends, and it's complicated.
They don't really talk about that.
Nope. Because of what Gabe is talking about is why if I gave every one of you guys, if you guys donated, let's say you gave me a pint of your blood and spun it down and just infused you back with your red blood cells, you would immediately run a mile a minute faster. Right? You can make your VO2 max go up 10% or something. Just like you wouldn't even do it. You're the same person, same muscle, same mitochondria, same heart. Your blood volume goes up, but your O2 carrying capacity goes way up. And that's why it's Armstrong. It's very right. And in some ways, you can make it out that they're all different. Every one of them are different. They have to be. You can't ride that much for 3 straight weeks and not die. You maintain that kind of performance unless you do it. So maybe Lance was still the best cyclist. Maybe he had the best doctor. So
He got caught, so.
yeah, but he's still a shit pile of a person that had to be like really beat over the head with things and ruined a lot of people's lives trying to defend himself before all that. But yes, he did get caught. Was it worth it? Y'all think all the money he's given to cancer research, was it worth all of the lying and cheating and ruining people's lives for all those millions of dollars he raised?
Good versus bad press.
Just saying. Sorry?
I didn't hear it.
He was said like that they're lying and got them fired from their jobs working for his team and took him to court and bankrupted him by saying I'm going to sue for defamation. You know, he has money and so he could defend and he could bring the lawsuits, right? And they can't defend yourself. So just Google it. And it's not good. It's not good. It's really good. Okay. Let me do a little bit of stuff on all of this. Yes, ma'am.
The same part size increases small, but like how quickly does it go through each week when you stop drinking? Is that instant? Or is that like months down the line?
It's not as fast as the atrophy we see in skeletal muscle because you don't get to a place where there's total disuse. If that makes sense.
Yeah.
Like unloading the space flight or bed rest or those things, skeletal muscle, we basically not using the muscles not being loaded ever. In the cardiovascular system, when the heart still beats, you're still contracting there, the blood pressure still goes up, but you're still, even if you're not running and training a bunch, you're still going to get some time during the day. You went up some stairs and stuff, it's going to have to work a little bit harder. So you're going to lose some. I don't know what, I'm not sure what the time course is. That's an interesting question. It's not as fast. If you lose it within like a week, skeletal muscle, you'll start. Heart's going to be smaller. Same with the mitochondria. Mitochondrial density begins to decline over time as well. But because you're always running metabolism, even if you're just resting, then you're still, it's going to be a slower process than what we see in absolute muscle.
And is it like a significant change? Or is it very small?
Like how much does cardiac hypertrophy do you see?
Yeah.
Oh, it's very significant.
Okay.
So I mean, 20%, 25%. It's significant.
So can that play a role in the age factor? Because obviously with heart rate.
Are you suggesting that I'm old and so therefore I have a smaller heart than you? Is that what
possibly.
you're saying? I'm the Grinch and I have a small heart? Is that what you're saying, Christina? Y'all
You
heard her
have a
say
better
that,
heart
right?
than I have a black heart. I've already said that a million times, so can't really say much.
Anyway, it's okay. I'm sorry.
I don't care.
You're just saying, so you're
Like,
saying.
does that play a factor in the
So,
age predicted heart rate?
no, it's not really a factor. You
Okay.
may have declines in stroke volume with age. So, one of the reasons that age matters in VO2 max is that your maximal heart rate, which is going to play a role in your maximal cardiac output that we haven't talked about yet. Your max heart rate declines with age as the SA node becomes less sensitive to epinephrine. So because of that, I cannot raise my max heart rate to the same extent that you guys can. Since my guess is that I'll be okay. The other thing that happens with age is there may be the left ventricle may shrink, therefore stroke volume goes down. The connective tissue and the cardiac muscle becomes less plastic, it's less stretchy. And so because of that, you can't, the preload can't get as high, that further makes stroke volume go down. And so now we're hitting cardiac output from both sides.
Okay.
In addition to the fact that I'm probably more sedentary than you are, age will predict that. So I have fewer mitochondria, my muscles as well. So yeah, there's a lot of things. In theory, if you can stay active and do things and you're an older person outside of the decline from cardiac output and heart rate, then if you normalize for that, people could be pretty much the same.
Okay.
You know, basically run out the clock on questions.
Sorry.
That's okay. Questions are good. Questions are good. Some of this I'm gonna mention, and this is a lot of this is kind of a prep stuff for our master students. They're gonna have Dr. Dunn's class, the exercise physiology lab class. You guys will actually do VO2 max tests on each other. And so how do we know if a person has reached their VO2 max? Remember, I told you guys that a plateau in VO2. So VO2 does not go up when the work rate goes up. That is the single best, the one kind of true criteria for denoting that we've reached VO2 max. Okay? The problem is that most people can't work harder to make this happen. And people that are even motivated, it's really hard, especially if it's not on the treadmill, because of fatigue. You're on the bike and your legs get tired, right? You fatigue a little bit before you can actually kind of max out what the cardiovascular system is able to do. So a plateau in VO2 is the best way to do it. In the absence of a plateau, what we recommend now for people to do is you stop the test, you rest for about 30 minutes, and we put you back on the treadmill or the bike at the work rate at which you ended the test. And then we let you go for a couple of minutes, then we forcibly increase the work rate. So we're forcing you to work at a higher rate because you can. You say some of your energy stores, but we can see if we can drive them to one. So one of my master students is going to do VO2 max testing as part of the thesis. We have to decide if that's what we're going to do. That's okay. We'll just do kind of. In the absence of a plateau, we've developed these what we call secondary criteria. One of them is a blood lactate level of 8 millimoles. You're at about 2 at rest. 8 millimoles is like 4 times what you see at rest. All this denotes, along with an RAR greater than 1.1, is that you really taxed anaerobic metabolism, which is going to give us a really good sense that you probably will be very close to maxing out the system. So 8 millimoles, where they got that number, I don't really know. Why is it not 10? Why is it not 12? Why is it not 4? There's some reason, but 8 is kind of the criteria level. We didn't talk about how your RER can get over 1. So one of the reasons, and we'll talk about this with the pulmonary stuff, that your RER can get over 1 is that when you start making a lot of lactate, you buffer the hydrogen ion in your blood with something called bicarbonate. And when you buffer it via bicarbonate, then you actually release some stored CO2 in your blood. And so you're releasing CO2 with the lungs that it's not directly being made in aerobic metabolism. So you've got extra CO2 that's come from anaerobic metabolism. And so your RER can get over 1. By doing all of that, or over 1.1 is what we're going to say. So again, these two things denote lots of anaerobic metabolism, which means we've probably got close to max CO2. RPE values of 19 or 20, who gives a shit? This is subjective. I can walk and tell you it's 20. It may or may not be, but people will use this. 90% of age predicted max VO2. This is fine, but our predicted things are all off because we're all sedentary now. And so 90% of what it ought to be is probably more like 95% of what people are going to kind of get at this time. And then the other one that really people care about are these two, and then the last one, 95% of age predicted max. That means we've gotten really, really close to maxing out right now. If we've done that, then we really should be very, very close. Here's some values. Quickly, average values in somewhat active college-age students or kind of young undergraduate college-age students. The men are going to be kind of in the mid-40s to about 50. To be really honest, these days, given the sedentary nature of stuff, it's probably 40 to mid-40s. Women are going to be right around 40, probably now 35 to about 40 in all of these things. Remember, see, I put here very much lower in 2011 because of our sedentary culture. I need to update this to 2021. That tells you how old this frickin' slide is. In elite distance runners, in men, we'll see values in the 70s and the 80s. The highest ever recorded this value in the men is wrong now. There was a European cyclist who actually was not that good, but I think he was at like 96 or 97 mLs per kg per minute, which is just a ridiculous number. And then women, it's about 77. These two values that you see here are actually cross-country skiers. Those are, if you guys know anything about people, anybody ever been cross-country skiing? Anybody ever been on the old Nordic track we had when I was little? Nordic track, it's like an ergometer that is for cross-country skiing. That shit is hard. Use your legs and your arms. So lots of extra muscle mass. That's why the values. So here are the elite. This is from the Costco study of those distance runners, the Olympians from the early 70s. Here's the elite, right? Here's our Olympians. Their average VO2 max is about 77. The college age middle distance runners were about 70, so see not a huge difference. These guys are Olympians. These guys are just kind of regular college folks. And here's our untrained guys that are about 58. Okay, so I've seen in people that we've tested in my time doing this, we've seen like 82 is about the highest we've ever seen. I've never had a woman get into the 70s. We've seen some women at about 68. On the treadmill. And so I've seen some that were in like the mid 60s that weren't very good. And you kind of throw your hands up to the cross country coach and go, I don't know, she should be really good. So there's some other things that are going on. She has the capacity to get a lot better. Okay, we'll stop here. We'll just keep plugging away on what these things are going to be on. Tentatively prepare for the test for next Monday. We'll see what happens on Wednesday. We'll make that. All right. Okay. Yes. I have